Welcome, and so we were discussing about the torque slip characteristics of a three-phase induction motor, and which is very important. It gives us an opportunity to understand how the machine settles down to a particular operating point, and under no load condition I told you it will be like this. Now, I will further examine what it is going to do if there is a real load torque present on the machine. So, let us imagine I will draw in a very large scale. So, that this always draw the torque slip characteristics correctly. Correctly means do not draw a torque slip characteristics of a well designed induction motor something like this, S equal to 1, S equal to 0. Students are often found that they draw it like this, and no, never draw, because the T max for a well designed motor will be close by S equal to 0. A typical value I told it is S equal to 0.1. So, just do not draw like this. So, this is the thing, and this is suppose S equal to 1, this point, and this is S equal to 0. And I told you also it is a good practice. So, this side is slip, and this way also you draw, this is 1, this way you draw speed, which is NR, and the NR value is just opposite, NR equal to 0, and this is NR equal to NS, like this. And then the torque slip characteristics will be somewhat like this. Initially it is very steep, and then it goes like this. This is T s, and this is T max, T e max, expression of which we know, and this is the slip at which maximum torque occurs, is called alpha. And I told you that if the opposing torque is friction, which is very little, suppose this is the level of T friction present on the shaft of the machine, this is T friction. You switch on the supply, this is your starting torque, and machine will accelerate, it will go like this all the way, and then it will finally settle down here, which is very close to synchronous speed, and machine is running like that, and then the machine is said to be running at a under no load condition. Of course, you have not purchased a motor to run it under no load condition. You want that your motor serves some mechanical load. For example, the motor will raise water to a tank at a certain height. Then really opposing torque will come, and there the mechanical torque will be developed, and the motor is going to do some mechanical work. Or suppose the motor is doing some rolling operation in a steel plant, then opposing torque really comes. Now, I will formulate. So, this is the no load speed n at 0, which is very close to n s. Now, let us imagine. So, here is your motor, and I will just show it like this. It was earlier running under no load condition. Here is supply you have given, just 3 phase supply, and it is running at n r 0 speed. Now, let us imagine on the shaft of the motor I have suddenly put some mechanical load. I ask the motor do some mechanical work for me. that is connect the external mechanical load on the shaft, no resistance, nothing like that, it is mechanical load. And therefore, let us imagine that at t equal to, so machine is hitherto running at n at 0 speed. So, t less than 0, the speed of the motor is n at 0, no load. Now, at t equal to 0, what I do? I increase the load torque on the shaft of the machine, that is the opposing torque. A step jump I give suddenly on the shaft of the motor. So, machine was nicely running here. Suddenly, I put this opposing load torque. So it is like this. From T friction, the net opposing torque is T load. So, this is T load plus T friction, whatever is there, that is there. So, this will be suddenly motor will see at t equal to 0 impose T L opposing, which is generally denoted by T L load torque. Okay. Suddenly I have put. So, machine was running like this and I have put an opposing torque. Now, what the motor is going to do? I told you motor is nothing but an inertia. It will accelerate provided the electromagnetic torque is greater than the opposing torque, or it will run steadily at some RPM when these two are equal, or it will decelerate if electromagnetic torque developed by the machine is less than the opposing load torque. These are the three things we know from Newton's laws of motion. Therefore, at t equal to 0 plus, at t equal to 0 plus, after you have imposed this opposing load torque on the shaft, can speed change instantaneously? No, speed cannot have a step jump. Speed will be at t equal to 0 plus immediately after you have imposed this opposing torque has to be n at 0 itself, or the slip cannot change instantaneously. Therefore, what will be the electromagnetic torque developed by the motor at t equal to 0 plus? It will still remain this value, because at this speed machine is still running at t equal to 0 minus, it was running at n at 0. At t equal to 0 plus 2, it will run at this speed. Therefore, electromagnetic torque developed by the motor is only this much at t equal to 0 plus, but the opposing torque is this much, because this I have suddenly imposed. There is no scope for showing time in this diagram, you must understand that. Time is in my mind. Okay. So, at t equal to 0 plus, n at 0 will remain n at 0 rotor speed, but you have imposed a opposing load torque, that I can show nicely here. And then I say, okay, at t equal to 0 plus, electromagnetic torque developed by the machine is less than T L. That is the conclusion, because at this speed opposing torque is this much and electromagnetic torque is only this much. Therefore, what the motor is going to do? Motor to decelerate, rotor decelerates. Now, rotor decelerates means speed decreases, therefore, operating point starts moving, speed will now decrease, this way it will move. A time will come when it will come here, Of course, because of inertia suddenly machine cannot stop, you must understand also this point. I will tell now in this diagram. Okay, because it was decelerating and suddenly that deceleration is stopped, will not happen because of once again inertia. So, what happens, motor may cross this way, it may cross this point where T load is equal to electromagnetic torque developed by the machine. Operating point may shift there, but the moment it crosses this point, I find T is greater than T load, therefore, it will accelerate. Therefore, maybe after few oscillations here it will go this way, then it will come, it will do few oscillations here. Of course, finally it will settle down there because the moment it comes, speed tide to decrease. So, operating point, machine always try to seek this point as its final settled point. So, after maybe few oscillations it will come here. So, once again you see this is the black one is the characteristics of the motor and load torque is the characteristics of the load, which demands constant load torque at all the speeds. Two things are entirely different, but if you superpose one above the other, then the point of intersections are important. That is, this is the point of intersection and machine will now run therefore, at this RPM NR, which will be further less than the no load speed, but nonetheless close by to Ns. Imagine you have increased the load further, T load 1, T load 2. Once again you have it was running here with supplying T load, you increase the opposing load torque further, then I know okay, arguing like this, once again machine will try to come and settle down here, is not? Increase it further, opposing load torque, operating point will come here and you know it will go on running at final speed, which is now less than synchronous and it is visible. I mean no load speed was very close to synchronous, but as you go on increasing the load, it will be running at lesser and lesser speed steadily. Okay. Now, in this way the opposing load torque can be increased. Of course, variation of the speed from no load to full load of course, the term I should not use, I am not told what full load is, but as you go on increasing the load torque, speed drops. But speed will not drop by a very large amount because of the fact this is only this value of NR, this is only 10% of NS, I mean some typical value, is not only by 10% the speed may change as you proceed like this, increase it will come run here, but this variation of speed or variation of sleep is only very little. Therefore, induction motors earlier days people used to say that it is a almost a constant speed motor like a DC shunt motor. If you do not touch field winding of a DC shunt motor, variation of speed from no load to full load is very little, almost like a constant speed motor, because variation of speed, if it is a 4 pole 50 hertz machine, it is 1500 RPM, 10% of that 0.1 only the speed may change by 150 RPM or so as you go towards that side. Now, coming to the full load torque, what is full load torque and how it should be decided upon. Okay, let us go ahead further. You go on increasing the load torque, operating point moves to the right, it comes here like that. Suppose you increase the load torque beyond the torque which the motor is capable of doing, maximum torque motor is capable of doing, that is T max. Suppose somebody says, okay, it is working here fine, but I will increase the load torque, opposing torque beyond T max. What is going to happen? Okay, if you are starting from this point, load torque greater than electromagnetic torque, machine decelerates, it comes here, load torque is still greater than T max even, speed will further decrease, and as you can see operating point moves like this, and as the load torque opposing torque you have made greater than T max, and at no point in this range 0 to 1 this trend is going to be reversed, that is TL is always greater than T developed whatever point you take. So, what will happen? Machine will finally come down to standstill. Therefore, you see this way, if you go on increasing load torque, when the load torque demand is greater than T max, then the final steady state operating point running at some RPM is not available, that operating point itself is not there, and machine will eventually come to a stop. So, the question is, when you increase the load torque on the shaft of the machine, you should be a bit careful. It looks like this one is 0.1 and another point. Suppose somebody has increased, okay, machine is capable of producing this much torque, okay, let me put this torque, it will run, and let this be called the full load torque, and machine is designed to run at this full load torque, then it will run at this speed. But this is not advisable. Why? Because this point is crucial, this operating point. As you move closer to T max and you do not know, there may come some disturbance. You are close to the vulnerable point, your load torque is close to T max, still less than T max, motor is capable of producing that torque. But as you closer to T max, you are running the risk, because motor is running, doing some mechanical work, but disturbance you cannot avoid. It may so happen that load torque has suddenly increased by a small percentage on this side, then you are gone. If by chance load torque increases by 10% or 20%, then this value, it crosses that dreaded point, that where machine will not be able to recover and give you a final operating point running steadily at some RPM. Therefore, it is quite advisable your load torque, full load torque you design such that it is not very near to T max. Although theoretically it is possible, one may design, okay, a machine is capable of developing T max, but is it prudent to do that? No, because disturbances will be always there. Load torque may suddenly increased this way, that way. So, people then say that okay, to avoid such a scenario, you design the full load torque, which is in the midway of this linear portion of the torque slip curve. This portion is closer to a linear relationship. We will discuss it further, but it is quite steep. In the linear portion and 50% of T max, and let us arbitrarily say that my full load torque I will never exceed, it will be close to 50% of T max. Better you do like that. Certainly, it cannot be close to T max, or no point in choosing a T full load here at this level close to synchronous speed. Then you are not utilizing the motor. Motor is capable of developing T max this much, and somebody says my full load torque is here, motor is not properly then utilized. So, keeping all these things in mind, people suggest that better design your motor full load torque 0.50% of say T max, such that the full load speed, it is, since this zone is almost linear, will be about I mean the slip value will be also about, this is 0.1. So, this will be 0.05 say. So, induction motors are designed at a full load slip, the slip steady state slip corresponding to full load torque TFL, which is here suppose midway between these two, is say slip SFL is equal to say 0.05. Then you have enough margin, because always remember that any electrical motors can be run overloaded for some time, is not? It is not that you overload the machine and machine will burn. 15-20% overloads are possible, but for a definite amount of time. Continuously do not run a motor overloaded. Then the question of burning of windings, this that comes in, because to burn a coil, suppose a coil rated current is 5 ampere. If I pass 10 ampere, do you think the coil will burn? It depends. If you pass 10 ampere, which is capable of carrying current 5 ampere, if you pass 10 ampere for long time, it goes. But 10 ampere for maybe 2 seconds you can allow, it does not matter, 5 seconds you can allow. Because you know, to burn a thing, you not only require the power, but power into time, how much joules you are trying to dissipate. Time is a factor, amount of heat generated is not only decided by I square R, also into time, how much heat, and that heat raises the temperature, breaks the conductor, burns it, this that. Therefore, overloading is a good engineering practice, provided one knows how much to overload and for how long time, that is most important. That is why, keeping all these things in mind, full load torque of a induction motor is operating point is decided somewhere midway between these two. It can be this way, that way a bit, 4% full load slip is also possible, you will see motors, but it will be of that order 4%, 5%, 6%, that is the full load slip, typical value of full load slip of a 3-phase induction motor. So, this zone, mind you, is very steep, then and this occupies only 1/10 of the scale about roughly, and then this is the rest of the things. Achha, after we have done, now see the interesting point. For example, I told you this point, I will draw it separately, so that you understand it better. So always draw torque slip characteristics properly, that is one thing. So, it is suppose the torque slip characteristics. Make practice drawing yourself. So, suppose this is a typical well designed 3-phase induction motor, the torque slip characteristics is like this. This is once again S equal to 1, this is S equal to 0, this is T max. Although here also I have not drawn properly, this should be 1/10 of this approximately, I mean this is T max. Acha, I told you at no load it was operating here, T friction suppose, and T starting was greater than T friction. Now, when I told that T friction is suddenly raised to this level, say full load torque level, suddenly a step jump at T equal to 0, I have done this. Earlier it was running at no load speed NR0, now suddenly it is increased, and we know the final operating point will be here. But we must now observe these two torque slip characteristics very carefully. One is because of the motor, this is motor characteristics, how much torque it will generate, and this is the load characteristics, mechanical load characteristics. It demands that no matter at what speed it is running, it requires a constant load torque. It means that. Now, you observe carefully, there are two operating point it looks like, because at these two operating points, the electromagnetic torque generated by the motor will be equal to the opposing full load torque present, mechanical load torque present. Therefore, it looks like that I have told till now, here also you see this is the full load torque, okay. There are, it looks like there are two operating points, why not it will operate here? While explaining I told okay it moves here, okay it did not reach there, before that it reaches, those things are fine, but what happens at this point? Let us try to explain that. So, suppose this is the full load torque, and let us for argument's sake assume that motor is somehow settled down at this point. Then if it is settled down to this point where it is absolutely fine, electromagnetic torque and opposing full load torque are equal, and machine will perhaps run at this RPM whatever it is, and it is at a very low RPM as you can see compared to this side. But this operating point is not stable operating point, not stable operating point. Why? How do you test stability? Suppose we say that a ball kept in a bowel, this is the floor, you have another bowel which is kept inverted, keep these two balls, this one is stable, this ball is not stable, critically stable, because a slight disturbance comes, wind blows, this fellow will roll down and it will never come back on its own to the original position, it cannot. But here it is, if suppose slight disturbance you give and release your hand, it will oscillate a bit, but once again come back here. So, this operating point is of this kind. Okay, these two are equal, it is critically stable, but a slight disturbance comes because you do not know. Suppose the speed has slightly dropped. What is the speed? Speed is this way. You do not know, speed may change a bit, n r equal to n s, this is n r equal to 0. Suppose speed drops a bit by some external factors. If speed comes here and the operating point then should be like this, if there is a slight disturbance in speed in this direction delta n r, then you see full load opposing torque is greater than electromagnetic torque. It will further decelerate, operating point will move like there, and there is no point where electromagnetic torque can match this full load torque present, and machine will come down here. Similarly, if there is a disturbance this side delta n r, you immediately conclude, electromagnetic torque is this and opposite load torque is this, motor will accelerate, and it will accelerate means it will go here, it will come here, still it is greater than, accelerate, and finally, this is the stable operating point, it will settle down here. Think about this interesting behavior of the machine. So, for a constant load torque, we then we may conclude that this zone is the stable zone and this zone of this unstable zone. We will discuss further about this. So, hope you have understood about the operating points and about the stable operating point and how the full load torque should be decided upon midway between 0 and T max approximately. That way it is designed so that you do not go close to a place where at the boundary stable and unstable zone meets, because that will be somewhat disturbing. A slight disturbance comes, motor will not operate, it will come to stop. So, think about these points and carefully go through this. We will continue from this point next class. Thank you.